Okay then, last week we looked at the basic formula for direct stress, or sometimes called axial stress, and that was force over area. I'll show it again to you in a minute, but just for your reference, the direct stress, and I normally use the Greek symbols, is that sideways 6 looking symbol, which is lowercase sigma, is equal to force over area. And we spent quite a bit of time looking at that formula, rearranging the formula and that kind of thing. And also I did mention to you last week something that might crop up again this week was factor of safety, FOS, and that was the maximum allowable stress, which could be the ultimate tensile strengths, it could be the yield strengths, divided by what's called the working stress, which is the stress you can have in the component every day of its life kind of thing, what's called the working stress. So we did play around with that a little bit last week. The factor of safety kind of crosses disciplines, it crosses areas, crosses topics, that factor formula. But the stress formula we looked at was specific to what we were doing last week, which was basically tension or compression in members. That's what we were looking at. And we'll recap that briefly on the next slide. But today what I want to do is introduce two more formulae to you, which some of you may have seen before, perhaps some not. The first formula we're going to look at, the new one, is direct, or sometimes called axial strain. Okay, direct strain, axial strain, same thing. Again, I'm using the Greek symbols. The formula sheets you use do have the Greek symbols in them. This is epsilon, it's lowercase epsilon, it's like a backward 3. And this relates to components that are in tension or compression. The direct strain is defined as this formula here, and that's the change in length, which could be an extension or a contraction, over the original length of the component. And again, I've got some Greek symbols here. Greek symbol lowercase delta, that's a very small d, curly d there, over the length of the object, which is L. So that's another formula that we're going to use. You'll see in the questions we're going to look at today, we'll bring in the previous lectures work on stress, force over area. This one up here, we'll be using this formula again, and we'll also be using this strain formula as well. Now, strain is dimensionless. I always keep on about you should specify the correct units after your numerical values, but strain is dimensionless because basically it's an extension or a contraction, which would be in meters, divided by an original length, which would be in meters. Okay, so strain has no units, it is a dimensionless value. Generally speaking, strains are very, very small, you'll find, so it'll be 30 times 10 to the minus 6 for a strain value. Very, very small values in metallic materials for strains. You'll see that again in the examples. And the final equation we're going to use today is relates to Young's modulus, or elastic modulus, and that's given symbol E. Okay, that's the final formula. Again, hopefully you've seen these in your materials lectures. Hopefully you've come across these properties before. Now, the E is defined as the stress in a component, the direct stress, over the strain, the direct strain in the components. In other words, it's the stress, which we looked at last week, shown above here for convenience, divided by the strain formula, which we've got above in this slide. And what you've got there are three equations now. It's one for stress, one for strain, and one for elastic modulus. They all relate to each other, they all kind of interrelate with each other. So just for your reference, the E value relates to the slope of the line. You may have heard of Hooke's law before. I know some of you have come across that. Hooke came up with this concept years ago, many centuries ago now, that stress was proportional to strain. That's what that symbol means, proportional there. So it was quite revolutionary, that was when it came about. So Hooke's law is stress is proportional to strain, but we really use that in the Young's modulus, or the elastic modulus formula of stress divided by strain. And I think it's called Young's modulus because I think somebody called Thomas Young did a lot of work on this. I think that's a historical background, I'm not 100% sure. So basically, from our point of view, what we've got are these three formulae shown on the page here. We've got the formula for axial stress, or direct stress. Stress is the force divided by the area, and the force is the, we often label it P in most sort of textbooks, P or sometimes F, but the force is applied, so that could be a pull at the end of the bar shown there, or it could be a push, compressive force. So P is plus or sort of minus, if you like, as far as forces are concerned. And the cross-sectional area of the bar, I've shown it circular section here. It can be any section, it can be circular, rectangular, square, whatever, is that area there shown. Okay, that's the area, so that's the P upon the A. And we just defined now the new formula for strain. Strain is defined as the extension over the original length, we just said. So axial strain is the extension, shown here as an extension. It's changing length really, but it can be shown as an increase in length over the original length, and that's the original length of the bar shown there, sort of a rectangular section bar there. And then we said the elastic modulus links the two together. That's the thing that links them together. The E is the stress over the strain, so they're linked together. Okay. Now, if these three formulae could go down the pub, they would go to the pub together. All right. Whenever you see them in a textbook or look at them on the internet, they're always together. They're best mates. Okay. So usually in a problem, when we use one of them, we find we normally use another of them. They do link together. And what you're going to find in the work we're going to do today is that we're going to, given the information in the question, we may start off possibly finding the stress. We may be given in the question the load applied, and we may be given some geometry so we can find the area. We may be given in the question the elastic modulus and the length. That may be given in the question, but we might be asked to find the extension. That might be what we need to find. What is the extension? So we may find the stress first of all. We may then take the stress and put it into this equation here, and then we may rearrange the equation to find the strain. Then we may take it from this equation into this equation, and we might rearrange it to find the extension, this thing here. Okay, so we may have that kind of process where we're going to jump through the various equations in different orders. Sometimes we may only use 2 equations to solve a problem, sometimes all 3 equations to solve a problem. But that's the kind of process we're going to go through. We're going to sort of have to think through the 3 equations together and then decide where we go to solve the problem. Okay, so I'll show you that more so when we come to the examples, but that's the sort of thought process that might be involved in some of the questions. And I've just put the nomenclature down here if you want it for reference. Stresses can be in newtons per meter squared or newtons per millimeter squared. Forces are always in newtons. The cross-sectional area could be in meter squared or millimeter squared. Strain, we said, is dimensionless. Change in length can be in millimeters or meters, and the original length in millimeters or meters. As long as we're consistent within a question, we use all meters in the question or we use all millimeters, that's fine. Okay, we must be consistent within one question that we use the same consistent units, that's all. Alright, so that's the sort of backdrop to what we're going to do using those equations in this presentation. Here's an example. Again, it's in your notes. If you want to look at your notes, you'll see example 3 is already there. I'll briefly outline this and then we'll look at some questions together. So in this particular question, we're given a steel rod of 10 millimeters diameter. So that's allows us to find the area. We're given the length. Notice that's in meters. So we'll have to make a decision as to what units we're going to use, millimeters or meters. We're told that it stretches 1.8 millimeters, so that's an extension in this case, and we're told that the pull, the force applied, is 10 kilonewtons. We've got to calculate in this particular question the Young's modulus or the elastic modulus for the particular steel rod here. So as always, the first thing to do is take the information from the question and make sure you've got the units consistent. So the rod diameter I've put in meters, I'm working in meters here, and the rod length L was in meters. So I got my consistent units there. The component stretches 1.8 millimeters. Again, I've put that in terms of meters. So 1.8 millimeters is 0.0018 meters. And the force in the question, the load applied, the P, is 10 kilonewtons. Notice I've written that as 10,000 newtons. In other words, I've accounted for the prefix here. Be careful, that's a kilo prefix, so that's 10 to the 3, and I've accounted for that here. So if I was looking at this with my 3 equations, I've got the stress is equal to the force over the area. My first formula. I've got my strain, that backward 3 looking symbol there, is the extension over the original length, and the thing that links them together, the E, is equal to the stress over the strain. So those are the 3 equations. Looking at this question, what it wants me to find? It wants me to find the elastic modulus. It wants me to find this thing. So I'll need the stress and the strain to do that. Now from the question, what am I given? Well, I'm given the P, the force, that's the 10 kilonewtons. I'm given the rod diameter, so I can find the area in a moment. That should be okay, so I'll be able to find the direct stress. In this question, I'm given the extension. That's a change in length, so I've got that. I'm given the original length, so again, I can find the strain, and I can put those two values then into the E equation to find the E. So that's my process through this question. Fairly straightforward process here. Find the stress, find the strain, find the E. Okay, and that's what's been done. If you look at the solution here in step 1, I found the area. I've used the formula pi d squared upon 4 to find the area. You might want to use pi r squared, but I found the area in meters squared. That allowed me then to find the stress, which is the force, the 10 kilonewtons in this case, divided by the area above. In the question, that gave me the stress in newtons per meter squared in this case. Then I could find the strain. Next thing, strain, I'm given the extension in the question, and I'm given the original length in the question, so I can find the strain. I put that as 0.0006. You'll sometimes find that written as micro strain in the industry. Engineers often use the micro symbol, the micro prefix, which is 10 to the -6, because often strains in metallic materials are really, really small, so engineers often talk about micro strain. So if you want to use that, you can. But 0.0006 is fine. And then once I've found both of those, I can just put them into the formula below. I know the stress above, that's the 127.4 times 10 to the 6. I've just worked out the strain above, the 0.0006. So I can now find the elastic modulus, the E, which is the stress over the strain. And there's my answer. E in this case is in giganewtons per meter squared. Again, don't forget these prefixes, they keep cropping up. That one there is micro, so that's 10 to the -6. This one here is giga or giga, however you want to pronounce it, and that's 10 to the 9. Okay, so just be careful, the prefixes will crop up. And that's the kind of question we're going to do. We're going to bring all three equations into play. They may not necessarily be that order. That's a nice order. We've calculated the stress, we've calculated the strain, we've calculated the E. They won't always be in that order, but we'll be using all three equations. I just put this slide in just for reference. I don't know if you've seen this in your materials work, but this is just for materials really. What it's showing us is some sort of basic values on a stress strain diagram. This value here sometimes is called the yield point of your stress strain diagram. What we're doing is loading the component up to the in a tensile test. So I don't have seen it, but normally I have a tensile test specimen, sort of something like this kind of thing. I can kind of sketch it, a metallic sort of specimen, and we load the end of the components. I mean, tensile test, compression a bit more difficult to do. So tensile test, and we've got some kind of cross-sectional area here, or maybe a circular section or whatever it's going to be. So we apply some force to the component, and that starts to increase the extension of it. Normally we plot load against extension or force against extension. So load would be probably newtons here, and this would be the extension in the millimeters. And we draw a stress strain diagram or a load extension diagram, and that's what we're showing here, this diagram. So we kind of load the component as we increase the value of force on the component, so the load increases and then the extension increases. And we can think of that also in terms of stress and strain. You could write this diagram as stress against strain. You get exactly the same shape, just different values. Stress against strain is also another way of thinking of this diagram, but it's normally drawn load extension in the test itself. Anyway, we load it up to a stage, and what we find is we get to this stage, which is called the yield strengths. And if we release the load at this stage, it then goes back to its original shape. It will go back to its initial shape, and then we can reload it again, and it will then increase its length and so on. But if we go past the yield point and we continue to load it, it goes into what's called the plastic state. Now if we let go of the load, if we reduce the load, it would stay in that state. It will stay in that length. It's gone plastic, if you like. And as I mentioned last week when we were talking about factors of safety, Going plastic can be a failure. It's not necessarily broken, well, it isn't broken. The component is still in one piece and it's actually quite strong, but it can be considered a failure. Going plastic is a failure. So when we talked about a factor of safety last week, the maximum allowable stress could be the yield strengths. But if we do continue to load it past the plastic section, we'll eventually see the stress distribution, the load extension curve do this. And this highest point in the curve here, this point here, is often called the ultimate tensile strength. That's when it's broken into 2 bits on the in the test machine on the shop floor. All right, ultimate tensile strength. So often given the symbol sigma UTS here, and this one can be called the sigma Y for sigma yield. That's a sort of notation that's often used for these particular locations. All right. So the ultimate tensile strength is failure. That's when it's broken into 2 bits. Okay, so your maximum allowable stress and your factor of safety we looked at last week in the previous lecture could be either of those, and that's given in the question as to what it would be. But highlighting these, because in the first question we're going to look at, it will talk about these 2 points on the stress strain diagram. But this gradient here, if I sort of did a sort of right angled triangle there, the gradient of that line is the E value. That's the elastic modulus or the Young's modulus value. So that's a tensile test, and those properties are particularly useful. One other point I would just mention is the yield strength is sometimes called the proof strength, because when you're looking at tensile tests, if I just do another diagram here of stress against strain here, curves materials do not often show this sort of blip in the structure. Most materials I've ever seen in the industry, they actually have a continuous curve before they fail. So you don't actually get a defined yield point. So what engineers sometimes do is use what they call a proof stress, and sometimes it's called a 0.2% proof stress strength, and that's where they draw a line at 0.2% strain. If I sort of 0.2% sort of parallel line would hit the curves there. So that would be what's called a 0.2% proof stress, where that's 0.2% strain. Don't worry too much about that. It's not going to be an issue to you. But I'm just saying sometimes the yield strength is called a proof strength. When you don't have a clearly defined yield point, you then go for this proof strength. So this is a very similar idea, but just for reference now. Okay, let's read the question. It says, the following data were recorded from a tensile test. So I'm just reading the information from the question here. The first thing is, we've got a tensile specimen. I'm going to draw that over here and give myself a little diagram, my own little diagram here. So a tensile specimen, try and draw it in 3 dimensions here. Question, the diameter of the bar is 20 millimeters. So on my geometry, I'll just write that 20 millimeters. So across here, the diameter, so it'll be a circular section we're talking about here. The diameter, I'll call it D, is 20 millimeters. I'm going to work in millimeters, I think, here actually. I'll work in millimeters. So 20 millimeters I'm given. We're given the gauge length. Now the gauge length is the really length of the specimen as far as we're concerned. The gauge length is 200 millimeters. So in this particular case, that will relate to the length of the specimen across here. So this length across here, I'll draw it out here kind of thing. That's basically the length of the bar, but it's a specimen here. So that's L, to use the symbol, and that's 200. And again, I'm going to work in millimeters in this case, 200 millimeters. Now, we're also given some information. At 50 kilonewton load, we had an extension of 0.18 millimeters. That's interesting information. That'll be useful in a moment. We're given a yield point also, the load at the yield point, and we're given the ultimate tensile load applied when it failed. So I'm going to do a little diagram here just to illustrate that information of what we've got here. So this is my little stress strain diagram or load extension diagram. I'll draw it here. Okay, so I'll call it P. That's in, I'll put it in kilonewtons, and that's the extension, and that will be in millimeters in this case. So this is my generic stress strain diagram, and I'll show the blip there. Okay, so going back to what we looked at in the previous question, then this would be the load at the yield point. That's the yield point. I'll call that PY if you like here. This would be the load at the ultimate tensile strength across here. I'll call that P, I'll call it UTS if you like, ultimate tensile strengths. So we're given in the question the load at the ultimate tensile strength was 127 kilonewtons. Here. The load at the yield strength, just reading from the question, is 79 kilonewtons. Okay. And then we're given this elongation at the 50 kilonewton load. Well, if the 79 kilonewton load was the yield point when it yields, then the 50 kilonewton load obviously is lower than that. It'll be somewhere down here. So if I put 50 kilonewtons. So at this 50 kilonewton load, what we're given here in the question is an extension which is 0.18 millimeters, 0.18 millimeters. That's given in the question. And that will be a useful point. We'll need that in a moment. So that's the information from the question given. If I just go back through that very quickly. The ultimate tensile load they've given, I should say. Okay, that was the 127. So that's this value here. That's given in the question. They've given us the load at the yield point, which was a 79, which is this one here. It's given. And they've also given us the 50 kilonewton load, and they've given us the extension of that. So that's what these two values relate to here. They relate to that piece of information. You'll see we'll need that in a moment for what we're going to do. So let's have a go at finding parts A, B and C. So part A. We're asked to find the yield strength. So find yield strength. That can also be called the yield stress if you want to also use the word stress. Often strength is used by engineers because strength has a sort of definitive value. Stress can vary, but strength is like one particular value. So yield strength is the stress, if you like, at the yield point. So this yield strength is used, but it can be called yield stress if you want to. So to do that, we'll be using this formula for the yield stress, and I'm going to use the symbol sigma y here, just to give it a little symbol. So the yield stress or yield strength is equal to the force at the yield point, I called that Py, over the cross-sectional area. That goes back to our stress is force over area, but I'm just talking about the yield point here. What's the stress going to be at which the component will yield? Well, we know the load at which it yielded because that was given from the test, but what's the stress at which it yields? And we get that from this formula. Now, of course, we're going to want to find the area here, so I need to do the area calculation. Perhaps I'll do that at the top of the screen to save space here. I'm going to calculate the area of the specimen. So area A. I'm going to use my pi d squared upon 4 formula. You might want to use pi r squared. I normally use pi d squared upon 4 because in all the questions I get given diameters, you'll see. Because you can measure diameter, you can't really measure radius so easily. So I'm going to use the pi d squared upon 4 formula. You want to use pi r squared, that's fine. I'm using pi multiplied by the 20, that's the diameter squared, divided by 4. Okay, you're going to use pi r squared, it'll be pi times 10 squared, of course. That gives me 314.2, and that's millimeters squared. Okay, so I'll let you do the calculation, you can check that out for yourself, but 314.2 millimeters squared. So we need the area, we're given in the question diameter, so we can find the area reasonably okay. So back to working out the yield strength. That will now be the force applied. So the yield strength force was 79 kilonewtons, so 79 times 10 to the 3, and that's divided by the area above of 314.2. Okay, so you can do the numbers on that, see what you get. I get 251.5, and I'm using newtons per millimeter squared for my calcs. Notice in the question it actually says 251 meganewtons per meter squared. We looked at that last week. Don't forget that's the same as the newtons per millimetre squared. So they're the same stress level but different units. So don't let that confuse you. 251.5 meganewtons per metre squared is the same stress level as 251.5 newtons per millimetre squared. It's just a different unit, that's all. And engineers use both of them, so I would get familiar with both here. That's the first part done. The part B. Part B wants us to find the ultimate tensile strengths. And again, if I use my symbols, I'm going to use that as sigma, and I'll just put UTS against it, ultimate tensile strength. So I'm finding this value up here, the red value, if you like, finding. Fine. That'll be the same formula, just different symbols here. So stress UTS is equal to, if I use the notation, that would be P UTS this time over my cross-section area. Area doesn't change. But I'll be using 127 kilonewtons, so 127 times 10 to the 3 newtons divided by the area 314.2. And again, doing the numbers on that, I get 404 newtons per millimetre squared, and again that's equivalent to, if you want to think of it as 404 meganewtons per metre squared. So again, they're equivalent to each other. So if you worked in meters, if your area has been in meters, you would get the 404 meganewtons per metre squared. We're working in an area of millimetres squared, so we get the 404 newtons per millimetre squared. But they're the same stress level, just different unit. Okay, now for part C, slightly more thinking required here. Let's have a little think about part C here. We've got to find the modulus of elasticity. So we've got to find the E value. So I'm just thinking out loud here, so you have to write this down. I've got to find E. And now we know that E is equal to the stress divided by the strain value. So I need to find the stress and I need to find the strain. Now can I do that? I need a point on my diagram where I can find the stress and the strain. And that's what I'm given with this 50 kilonewton load and extension of 0.18 millimeters. I'm actually given a point on the curve where I could find the stress and I could find the strain. And if I could find the stress and the strain at that point, and knowing it will start from 0, 0, I can effectively find the slope of that line, because the slope of that line, of course, is the E. That's the elastic modulus. Back to Hooke's law again. So I'm going to use that formula here, stress over strain, to find E, but I need to find the stress at that point, and I need to find the strain at that point on the diagram highlighted in yellow. Yeah, so part C, we've got to find the elastic modulus. Symbol E. So E is equal to the stress over the strain, but we need to find the stress and the strain. So where in this case the stress is equal to, so I'm going to use this P upon A formula, but I'm going to use the force of 50 kilonewtons, so 50 times 10 to the 3. And I'm going to divide it by the area, which will be the same as in the other question, so 314.2. So that will give me my stress. What I'm doing, 159 newtons per millimetre squared. And then the strain, I do the strain over here, is equal to the extension over the original length, and that's 0.18 from the diagram above divided by the 200, so that equals to, in my case I'm using micro strain, so 900 times 10 to the negative 6, but you may want to put that as 0.0009, it's the same value. So E is equal to the stress divided by the strain. Put it down again for. So the stress in this case was 159 newtons per millimetre squared, and the strain was the 900 times 10 to the negative 6 I'm using here, and that gives me 176.6 0.7 times 10 to the 3 newtons per millimeter squared. That's sometimes written in terms of kilonewtons as well, so it could be 176.7 kilonewtons per millimeter squared if you want to write it like that. Okay, so that's my final answer for the elastic modulus in this case, the 176.7. And that's the E value. So what you've got there on that those calculations are the three material properties you would need when you're doing calculations in industry: the yield strength, the ultimate tensile strength, and the E value. They're the typical three values used when you're doing strength analysis questions. So question 14. We've got a rectangular steel bar, 100 millimeters by 12 meters cross section. We've got a length given of 3 meters, subject to an axial tension load of 130 kilonewtons. We've got to determine the extension of the bar and given the Young's modulus. So lots of information here. So first thing I'm going to do is draw my diagram. I always like to have a diagram. A rectangular steel bar, and it's got some geometry here. It's a 100 millimeters this way. So that's my 100 millimeters, and it's a depth of 12 millimeters this way. And I'm using millimeters here because if you look in the question, can you see that the steel elastic modulus is given is kilonewtons per millimeter squared. If that had been in meters squared there, I'd put my geometry in meters. But as it's in millimeters squared, I'm going to keep my geometry in millimeters. So 100 millimeters by 12 millimeters, and I'm just getting that from the question. That's the geometry given in the question, all right? Don't forget that relates to the cross-sectional area. So that's, imagine you're sort of hacksawing through the component. And remember, that's what you would sort of see here. You would hacksaw through, that's the shape you would see. So that's the sort of area that we're going to calculate in a moment. That's the cross-sectional area there. Okay, we can quite easily work that one out. The length of the bar, so the length of the component, in this case, across here, is given as 3 meters. As I said, I'm going to use millimeters. That will be 3,000 millimeters is going to be the length of the bar. And again, I'm just getting that from the question. That's the length. So just taking that information out of the question. So put that into millimeters in this case. Okay, what else have we got? The tension load. It's in tension, this component, so that means there's a pull. So that's given in the question. It's given in terms of kilonewtons, so I'm going to take the prefix off. So 130 multiplied by 10 to the 3, and that's newtons. All right, so again, just taking the information from the question, and that's the tension load or force, if you want to call it P here. We've got to find the extension of the bar. How much does its length change when it's pulled, given the Young's modulus. So we're given the Young's modulus here. The Young's modulus 210 kilonewtons per millimeter squared. So I'm going to write that. So given elastic modulus, symbol E. And I said I'm going to take the prefix off, so that will be 210 multiplied by the kilo, that's 10 to the 3, and that's newtons per millimeter squared. So that's, I need to write this down. I'm just got to do my little sort of bit of thinking here, my little face here. It's supposed to be beard. Right, just do a little bit of thinking here as to how to tackle the problem. Now, these three equations always go together that we've been looking at. The stress is equal to the force over the area. The strain, I'm using the symbols for convenience, is equal to the extension over the original length. That's supposed to be a D, little d, over the original length. And then the thing links them together is the E is equal to the stress over the strain. Okay, they all go together, these little these equations. All right, so I just place them down there. And all I'm going to do is sort of tick off information that I know from the question. What do I actually know from the question? Well, I know the P, because I can clearly say I'm given the P in the question, and I know I can calculate the area because I've got the geometry. So I can find the stress in this case, the direct stress, straight away. Now the question wants me to find the extension. So that's what the question is after, determine the extension. Now in my symbols, the extension is here. What's this value going to be here? That's what I'm trying to find. I know I can find the stress, but I can't find the extension from the middle formula because I don't have the strain, this symbol here. I don't have that strain. So that's no good. So what else am I given in the question? Well, I'm also given the elastic modulus. I'm actually given the length as well. And I'm given the elastic modulus there. Now, because I've just worked out the stress there, I could put that stress value into this bottom equation, put it into there, and I could work out the strain by transposing, because I've got the E given to me in the question. So I can transpose to find this strain value. And then I could put the strain value into the middle equation here, and I could rearrange to find the extension with a transposition. So that's my kind of thinking steps through the process. You don't need to write that down. That's just the way I'm sort of thinking the questions through. I'm going to find the stress first of all, because in the question I'm given the P and I'm implicitly given the A, so I can find the stress. I'm also given in the question the elastic modulus, so from that I can find the strain, and I'm also given in the question the length, and from that I can find the change in length. So let's go through the process of finding first of all the area. We're going to need the cross-sectional area, so let's find that first of all. Make that my first step in the process. So step 1, find the area. So area is equal to, quite easy in this case, it's going to be 100 multiplied by 12. So 1200 millimeters squared is my area. So nice straightforward calculation to find the area. I need that. Now I can find the direct stress. Thinking back to my thinking little steps here, I can find my stress. So I'm going to make that step 2 here. So stress is equal to the force divided by the area. We're given a force in the question. It's 130 times 10 to the 3 newtons. And that's divided by area. Just calculate the area, so divided by 1200. So 108.3 newtons per millimetre squared. That's my direct stress value. According to my little calculations over here, I need to next find the direct strain for my thinking steps here, and I'll use the elastic modulus formula to find that. So step 3, find the direct strain. Now I'm going to use the elastic modulus formula, so from the E is equal to the stress divided by the strain. Okay, I know the E in this case, and I've just worked out the stress, so I can transpose to find the strain. So therefore the strain is epsilon. So a bit of transposition, we can do the transposition. You multiply both sides by the epsilon, divide both sides by the E, so that will be the stress divided by the E in this case. From above, the stress is at 108.3, and the E, which is given in the question, is 210 multiplied by 10 cubed. So I can work that one out. That's giving me the strain. Again, that will be a very, very small value. I've got a value of 516 times 10 to the negative 6. There's no units there. So that's a strain value. Okay, so I've got my stress value calculated, and I've got my strain value calculated. Now I can find the extension. So again, we'll do a transposition from the strain, this is my second formula in my list, is equal to the extension over the original length. So that's an S, but it's supposed to be a D. Then transposing the equation for delta, the extension is equal to, multiply both sides by L, in other words, the strain times the length. We said the strain was 516 times 10 to the negative 6, and we're multiplying that by the length, and that's given in the question. In millimetres it's 3000 millimetres, so therefore I can find the extension, which I get about 1.55 millimetres. Just check that out for yourself. Okay, that's the extension of the bar. So these are quite complicated problems you can see here, but they're all based around these three equations. But again, the more you do of them, the more you start to see the variations that it can be applied here. Just note for reference, this should actually state step 4 in the process, not step 3. Okay, in question 15, we're given a concrete cube as a side of 150 millimeters. I think we looked at a concrete cube question last week in the previous lecture. So a concrete cube has a side of 150 millimeters and was found to fail under a compressive load of 600 kilonewtons. So we'll be able to work out a compressive stress, basically, that's what that means. Now we've got to determine the maximum force that a column of the 300 millimeters diameter can withstand if it's made from the same mix of concrete and it has a factor of safety of 4 applied to it. The column's initially 6 millimeters in, the column is initially 6 meters in length, and we've got to find out how much it will shorten under the load applied. We're given the elastic modulus for the concrete. There's a lot of information there. Basically that question is in 2 parts, a bit like the question we looked at in the previous lecture. We're going to deal with the concrete cube first of all. Don't forget these concrete cubes are used as samples of a concrete mix, because concrete is quite variable in its properties, and that will be sent to the test house to find the strength of that mix, and then we would know when we're designing the column, which is the second part of the question, how strong the concrete mix was, and that will then indicate how much load we can put on the column given a factor of safety of 4. So it's like 2 little parts to the question. The concrete cube bit to look at first of all, and then we're going to design a column with the mix of concrete given. Alright, so let's see what information we can drag out the question. So first of all, we're talking about a concrete cube. So I think I'm going to draw a concrete cube. I'll draw it at the top of the screen, I think. And I'll get my information off on a concrete cube. So little concrete cube. And I said these are given to the test house. You'll sort of be laying your concrete, and then you would put a little bit of concrete. It used to be in days gone by, it used to be in a little wooden container, 6 inches by 6 inches container. We've got the geometry of it, so it's a cube, so every side is 150 millimeters in length. So that's my concrete cube, and it failed under a load of 600 kilonewtons. So basically what they're saying is they're applying a load P of 600 times 10 to the 3 to this object, this cube, and it failed under that load. Alright, so put P as well as P top and bottom, but it failed at that load. So the first thing we're able to do here is to calculate the failure strengths of this component, this cube. Now don't forget we'll be after the cross-sectional area here, and that will be sort of through here, the cross-sectional area. So we'll do it in shaded. That's the cross-sectional area we'll need. We'll need to work out that area of the concrete cube. Just all I've done so far is really taken this information out. The 150 millimeters, that's the concrete cube there, so that's my 150 for my concrete cube. And they've given me also in the question the applied loading, so that was the compressive load there, 600. So I've just taken that information from the question. That's all I've done so far, just like that first line. Now we've got to find the compressive stress from that first part of the question. Right, so part 1. So find the failure stress of the concrete cube. In other words, using last week's notation, that'll be the maximum allowable stress. We called that sigma max last week, because it cannot take any more load than that. It's failed. It's in bits on the test. All right. So that's the maximum possible load you could apply to a concrete cube before it fails. And we obviously don't want to work to that level. So that's why the factor of safety is stated later on. But for the moment, let's find the stress in the concrete. So the maximum stress, the failure stress of that little concrete block would be the force over the area. We know the force is 600 kilonewtons because it says that in the question. So we applied that force to the concrete cube and it crumbled. And the area will simply be 150 squared. We're talking area here, so it's 150 by 150 millimeters. So that will be, put the numbers in, 600 multiplied by 10 to the 3, and that's all divided by 150 times 150 gave me a value of 22,500, and that's a maximum allowable stress then of 26.6 recurring, so 26.7 newtons per millimeter squared. Okay, so that's what that first piece of information gives me. Almost that first line. I know the failure load, I know the geometry, so I know the cross-section area, I can find the failure stress. So if I was to draw a stress strain diagram for that on the right hand side here, so stress against strain, for concrete I just probably find, I'm drawing it in the tension sense of the diagram, but really obviously the compression, it fails in compression. What we're saying is it would load it up to the load of the 600 kilonewtons, and then it would fail at the stress level shown here of 26.7. That would be its failure stress. All right, that's the stress strain diagram. I'm drawing it in sort of a tension mode. As I said to you last week with the lectures, I don't at this level distinguish between positive and negative forces. It is really a negative force. That 600 kilonewtons really should be negative because it's a compressive force. But I use the context of the question to decide whether it's negative or positive. All right, but you may find in some textbooks they would put that as negative 26.7 newtons per millimeter squared, because it's a compressive stress, so we normally use negatives. But to save any confusion at this particular level, I'm just going to call that the 26.7 newtons per millimeter squared. But it is a compressive stress. All right, we are talking compressive stress. So let's read on then. We've been to the test house. We now know what the strength of the concrete mix is. The question goes on to say we're going to design a column from this material of 300 millimeters diameter, and we've got to apply a factor of safety of 4 to the column. Okay. Now don't forget from our previous work we looked at in the previous lecture, factor of safety is equal to the maximum allowable stress divided by what's called the working stress, the stress you can work the component to every day of its life. Now in this particular question they've given us the factor of safety. That FOS is actually 4 if you read the question. So there, factor of safety is 4, so we know this value is going to be 4. We just worked out the maximum allowable stress in the question, which is the 26.7, so I've got the maximum allowable stress. What I can do by rearranging the equation is find what's called the working stress for the component. So on the next line here, working stress, the sigma stress is equal to the maximum allowable stress divided by the factor of safety. So in this case that will be the 26.7, rounded that there, divided by 4. And that gives me about 6.7 newtons per millimeter squared. A little bit of rounding going on here, I know, but it'll be good enough for what we want. 6.7 newtons per millimeter squared. So that's the working stress. So if I go back to my diagram here, what I'm talking about is a stress level down here at 6.7 newtons per millimeter squared, where we're allowed to work the component up to. So we can work the component every day of its life into this region here, and we know it's got a lot of reserve in the material. It doesn't actually fail until 26.7, so we've got a factor of safety of 4. That means the column is 4 times stronger than it needs to be, if you want to think of it that way. So it's got a nice bit of strength to it, but it's also 4 times heavier than it needs to be. So sometimes a trade-off between sort of weight and strength kind of thing. Now I'm going to look at the column. The column geometry is given in the question, my concrete column. What we told about the column, we're told it's 300 millimeters diameter. Now again, I can see that the elastic modulus in the question is in kilonewtons per millimeter squared, so I'm going to keep that in millimeters in this case then. I'm going to work on my dimensions in millimeters. So the diameter of the column here, D, is 300 millimeters. What else am I given in the question? I'm given the length of the column. I know how long it is, the column, the length across here. My length here is 1000 millimeters. And what else am I given? I'm given the elastic modulus, and that's 20 kilonewtons, so that's times 10 to the 3 newtons per millimeter squared. Just taking that from the question. What we've got to do is calculate the maximum compressive load that the column can take. So determine the maximum compressive load or force that the column can take. So P is an unknown value in this case then. We don't know what the P is going to be. Obviously compressive, so we don't know the P. P on here as well. Got to find the P, and also we've got to find the how much the column will actually shorten as well. Wants to know how much the column will shorten, so something else we have to work out a bit later on. So how much will it shorten? I'm going to do my little thinking steps here, so I'm back to my thinking again. So put my three equations down. I've got stress equals to the force over the area. I've got the strain is equal to the extension over the original length, and I've got the E is equal to the stress over the strain. Just thinking this through. So what they asked me to find in this particular question, they want me to find the force. First of all, what force can the column take? P. So I can actually find that directly. When you think about it, I can find that directly because I'm given the diameter, so I'll be able to find the cross-sectional area, and I've just worked out the working stress that the column can be worked to, so I can find the P directly from using that equation, just a bit of transposition, so I can do that straight away. That's not a problem. What else do they want us to find in the question? They want us to find how much the column shortens. Now the column shortening this value here, I'm trying to find this value, how much it shortened. So what do I know in the question that will help me do that? Well, I don't know the strain at the moment, but I do know the length that's given in the question. I do know the E that's given in the question, or I've just worked out the stress in the question, so yeah, I can find the strain here. And I can put that strain into this equation, and I can rearrange to find the change in length. So again, that's my thinking little exercise through the question. You don't need to write that down, but that's how I'm thinking here, thinking it through here. I'm going to find the force from the stress equation, I'm going to find the strain from the E equation, and I'm going to find the extension from the strain equation. So there's my little process through the problem here. We're going to find the force. That's P. So from the stress is equal to the force divided by the area, I'm going to rearrange that equation, so therefore the force will be the stress times the area. So area of the column, I'm going to do that here. So my area is equal to pi, I'm going to use pi d squared upon 4 again, which is equal to the pi, and the d in this case is 300, so multiplied by 300 squared divided by 4. So my calculator, then my area will equal to 70,686 millimeters squared. So I can put that into my equation here. So the working stress is 6.7 newtons per millimeter squared above, multiplied by now the 70,686. 471.2 times 10 to the 3 newtons, or 471.2 kilonewtons, whichever you prefer to write down. So part 3, find, that would be that symbol delta, going back to our equations. So now what I'm going to have to do is find the strain, looking above in my little sort of thinking process. I'm going to have to find the strain from the elastic modulus formula. So from E is equal to the stress divided by the strain. Don't forget we've got the E in the question and we just worked out the stress, so I can rearrange the equation, 3 variable transposition. The strain will equal the stress divided by the E in this case, and that equals to, again that's a very small value, 0.0003 if you want to put the actual value down, or if you want it in sort of micro strain, it's 3.3, so that's a recurring number, and that's times 10 to the minus 6. Okay, both are correct, whichever you want to use there. But it's a recurring number there, so be careful, it's recurring on the 3 there. From the strain is equal to the delta over the original length. Again, I'm going to transpose that, so the is equal to the strain times the L. And that gave me a value of 2 millimeters. So it moves 2 millimeters underneath this applied load. And this is actually very similar to, I think, question 14 actually, in its process here. The only thing that's different is it's got a tube involved, an actual circular section. Let's see what we can do with this one. So a hollow steel tube, 100 millimeters external diameter and 80 millimeters internal diameter, is 2.5 meters in length. We've got to determine the extension of the tube if it's subject to a tensile force of 400 kilonewtons, and we're given the elastic modulus of 200 times 10 to the 3 newtons per millimeter squared. Okay, so taking the information from the question, here we've got a tube, so I like to do my own diagram, so I'm going to draw myself a tube section here. Okay, so that's the diameters we've got here. Alright, given in the question. So that's taken the geometry from the question that we're given, and put that there and there. What else are we given in the question? We're given the length is 2.5 meters long, so let's draw that. 2,500 millimeters in length there, and we've got a force applied. We've got the force is given to us, and P is equal to 400 kilonewtons. So 400 times 10 to the 3 newtons. There. Okay, and the elastic modulus we're given as well. We need to note that one. The E value is given in the question. Okay, if I just do my little thinking steps here for a moment, if I tick off what information I know in this particular question, what do I know? I know the P applied, I can find the area, I've got the formula, I've got the geometry, so I can work out the stress in a moment. What else do I know? I know the lengths in the question. I'm trying to find the extension, of course, if I should highlight, I'm trying to find the extension here. I know the lengths, but I don't know the strain, so that's no good. And I know the E, that's given in the question as well here. So what's my path through this? Well, I'm going to find the stress first. I'm going to put the stress into the E equation here, from which I can find the strain then, this value here, and I'm going to dump the strain into this equation, and then I can work out the delta, which is what the question wants me to find. What's the change in lengths? Okay, so you can really have a go at this yourselves, to be honest with you, because it's following now the same kind of process as we've done in previous questions. And that's worked out the extension of the column. I get about 1.77 millimeters ish, a bit of rounding maybe there. But that's the kind of process we would go through to find the extension in that case. Okay, I'll leave you with question 17 here. Read the question very carefully, there's lots of information here. Extract the values carefully, make sure the units are consistent, and go through the process of calculating first of all the elastic modulus, and then also we've got to calculate the contraction of the post. This has similarities to question 13 to begin with when you're working out the elastic modulus. And finally question 18. Read the question very carefully, extract the information from the question as usual and draw your diagram, but there's a very similar approach to that we've used in question 14 and question 16.